Okay, so in this lesson, we're going to be looking at box and string problems. This is a favorite of College Board, and what it's going to be is essentially two masses that are connected by a string. In this particular example, we're going to have two boxes that are connected by a string. College Board usually talks about there being a massless string that does not stretch, things of that nature. One of those lovely, wonderful, impossible strings that only exist where unicorns and fairies play. But in this case, we have a 5 kilogram mass attached by one of these impossible strings to a 10 kilogram mass. There is a 10 Newton applied force to the system, and most importantly, both of these masses are sitting on another impossible surface, a frictionless surface. Now, on the problem, we're going to be answering two questions. Question number one that I want you to determine is, what is the acceleration of the 5 kilogram mass? And then once we do that, we'll actually be comparing the acceleration of the 5 kilogram mass to that of the 10 kilogram mass. So question number one, what's the acceleration of the 5 kilogram mass? The second question that we're going to be dealing with is, what is the actual tension in the string? Now, there are several steps in solving these problems. So we've got an initial scenario here. It's involving forces. So step number one or step A in this case, is going to be the first step really in any problem involving forces. And that is going to be to draw a free body diagram, an FBD if you will, a free body diagram. Alright, now we're going to start here on the 5 kilogram mass, and we're going to start with the one force that's always present, and that would be gravity. This box is in contact with a surface, so there's also a normal force. Now, I want you to notice how I labeled these. Because I've got two masses, I can't just label the weight as mg. So I'm going to indicate that it's the mass of the 5 kilogram mass there, so we will label it as M5G. And because I've got two masses, I'm also going to have two normal forces. So I'm going to label this first normal force as N5. That means it's the normal force of the 5 kilogram mass. And then the next force I'm going to label here is the tension force, the tension in the string. Since there is no friction involved and there are no springs attached to this, that is, ladies and gentlemen, the free body diagram on the first mass. Now, looking at the 10 kilogram mass, and I'm treating these separately and individually. I have the weight of the 10 kilogram mass. Again, I've got to provide a unique label, so M10G. And here is the normal force of that 10 kilogram mass. I also have the tension, and I'm just going to color in the applied force there. So first, draw a free body diagram of each individual mass. That's just so we can kind of get oriented and see what's going on. I want you to notice the two tensions. They are both in the same rope. The two tensions point in opposite directions. This is considered to be an internal force that will ultimately cancel cancel each other out. So step A, draw a free body diagram, and we have done so. The next thing, step B, find the acceleration of the system as a whole. So here we go, find the acceleration of the system. Now, here's where we are going to deal with what a system is. First of all, I'm going to treat everything as one gigantic mass. Alright? And that means I have to find the total mass. Okay? So I have the 5 kilogram mass plus the 10 kilogram mass. Okay? And that equals 15 kilograms. Alright. And then we will just add that here on our picture. So first of all, the system, I have to treat everything together as one gigantic mass, which first of all I have to find total mass, which we have now done. The next step is a free body diagram of the system. Alright, free body diagram of the system. I don't have to worry about any internal forces. I only worry about external forces. Alright, so here is my first external force, the weight of the system. The entire system is in contact with the surface, so I do have a normal force. There is no friction, there are no springs. The system as a whole is not attached to an outside string, so that's pretty well it. I do have my applied force of 10 newtons. So, as always, the next step, now that I've drawn my free body diagram, is to start solving for net force. Alright, so, before I do that, I do want to talk briefly about the weight, and I just want to remind you, how do we solve for the weight? Well, the label tells us. It's mass times the acceleration due to gravity. This is sometimes important for these, sometimes not, but this is such an important concept, I feel like I need to go ahead and just remind everyone that we can solve for the weight of the system. And in this particular case, because it's on a horizontal surface, these two are indeed equal to one another. Now if I look at the net force in the x direction, I only have one force. It is the applied force, and it is 10 newtons. If I look at what's going on in the y direction, I have the normal force, I have the weight in the negative direction, and those add up to 0 newtons. Now, what I need to look at is the actual net force of the entire system. And I know what that net force is equal to. It's equal to m times a. And again, I want to remind you that this is of the system. This is the net force of the system, this is the mass of the system, and this is the acceleration of the system. And it is that acceleration of the system that I am most interested in. So I'm going to go ahead and rearrange this equation. And I have the acceleration of the system is going to be equal to the net force of the system divided by the mass of the system. So I'll just go ahead and fill that in. The acceleration of the system, therefore, is going to be, now since I don't have any net force in the y direction, the only net force comes from the x, which I know is 10 newtons. I'm going to divide that by the mass of the system, which is 15 kilograms. And 10 divided by 15 is 0.6 repeating. I'm going to go ahead and round that to 0.67 meters per second squared. So, the acceleration of the system is 0.67. Now, what I really need to do is I need to, once I solve for the acceleration of the system, it would be most beneficial if I now applied that acceleration to each of the individual masses within the system. Okay. So here's the next step. Apply the acceleration of the system to each of the individual masses. Sorry, I kind of misspelled on that, but to the system, apply that acceleration of the system to each individual mass. So let's go ahead and do that. I'm going to go ahead and redraw the original scenario here. So I've got my two masses attached by string. Here is the 5 kilogram mass. Here's the original 10 kilogram mass. Let me just go ahead and draw my forces back in. There's my 10 Newton applied force. Here's the weight, the 5 kilogram mass, the normal force, and the tension. Here's the weight of the 10 kilogram mass, its normal force, and tension, and I'm going to go ahead and color in the applied force here. Now, let's talk about the acceleration of the system. Alright, if you are driving in a car and the car is accelerating 2 meters per second squared, and you're inside of it, if the car accelerates that quickly, I hope it makes sense that you, as part of the system, are also accelerating at that same rate. And we have an acceleration of 0.67 for the system here, and since that's the acceleration of the system, everything within that system must also be accelerating at that same rate, including our 5 kilogram mass and our 10 kilogram mass. So the acceleration of the 5 kilogram mass is also 0.67 meters per second squared. The acceleration of our 10 kilogram mass is 0.67 meters per second squared. Alright, so to answer the original question, question number 1, which was this, what is the acceleration of the 5 kilogram mass? Well, we just answered it. It is 0.67 meters per second. It is the same as the acceleration of the system. Alright. In fact, the acceleration of the system is the acceleration of each individual thing. I could have asked you for the 10 kilogram mass and it would be the same thing. Now let's talk about solving for tension. Choose a mass, either one, the 5 or the 10, and you're going to apply Newton's second law. Okay, F equals ma. We're going to solve for both just so that you can see that it's essentially that it is going to be the same. We're just going to prove that point. But here's what I would recommend. Choose the mass with the least number of forces. In this case, it's the 5 kilogram mass. There are only 3 forces, whereas the 10 kilogram mass has 4. I would recommend that you choose the one with the least number of forces. We'll start with that one, and then we will proceed. And let's start with that 5 kilogram mass. I'm going to redraw the free body diagram here real quick. I'm going to apply Newton's law. I know that his second law. I know that all the forces in the y direction add up to 0. I've only got one force in the x direction. It is tension. It's not equal to 0. It is equal to mass times acceleration, and I know that acceleration. It's 0.67 meters per second squared. So, let me fill this in. I know that the tension, or the net force, is equal to mass times acceleration. The mass is 5 kilograms, and the acceleration is 0.67 meters per second. I can multiply those two together, and I can solve for the net force, which is again the tension, since the other two forces, the weight and normal force, cancel each other out. And that is going to be 3.35 newtons. 3.35 newtons. So there's the tension. I'm going to go ahead and solve for the box. I'm going to go ahead and separate this out. Here is the 10 kilogram mass. Let me go ahead and add in the forces. There's the weight. There's the normal force. There's our applied force of 10. Here is the tension. Again, the acceleration is 0.67 meters per second squared. Let's solve for the net forces in both the x and the y direction. All the forces cancel out in the y direction, they add up to 0. In the x direction, however, I have the applied force minus the tension. That's not equal to 0, that's equal to m times a, and that's what I want to focus in on, that segment of the equation. The applied force minus the tension is equal to mass times acceleration. If I rearrange the equation and solve for tension, I get the following. Applied force minus ma. Applied force is 10. The mass is 10 kilograms. The acceleration is 0.67. So when I multiply all this out, I have 10 newtons minus 6.7 newtons, and that gives me 3.3 newtons as the tension. Now, why the discrepancy here? I did want to talk about this. These tensions are in reality exactly the same. The reason I'm getting a little bit of a discrepancy in the answer here is simply because of the rounding involved in the acceleration. The acceleration is not 0.67, it is actually 0.6 repeating. So had I used 0.6 repeating in my calculations, I actually would have gotten the exact same tension in either case. So in review, basically if you have a box and string problem and you have to solve for a tension, which is ultimately what College Board is going to ask you to do, or solve an acceleration of an individual mass within a system, the key to solving this is to find the acceleration of the system. To do that, you determine the total mass, you apply Newton's second law, you write net force equations, solve for the acceleration, and then apply that acceleration to each individual mass. I hope you do well on these. The next lesson will involve two masses attached by strings, but one of the masses will be hanging off of the edge of a horizontal table, and it's the next level of difficulty. So we will apply that to next lesson.